Yeah, so just the final arguments to show that this is a decision procedure has to establish so-called completeness. In other words, if I start with an unsatisfiable clause, then eventually my resolution procedure returns true. Yeah, this is what we want to somehow establish. The question is, how could this possibly go wrong? Yes, Mark?
It wasn't the word, that was an example. What do you mean?
Well, it didn't actually go wrong there. Of course, you mean this example down here, yeah?
Yeah.
Yes.
Computation isn't complete there.
It's not incomplete because after you noted that that you got nowhere, you just try out some other stuff. So eventually you'll get there.
So it isn't by the algorithm, or
Not necessarily. I just want you to think. Okay, let's look at the algorithm again. So if this algorithm is not complete, what does that mean? It means I started with an unsatisfiable formula. The algorithm terminated, but it gave me the answer no. It's not unsatisfiable. That is.
You simply didn't try out all the possibilities.
Yeah, but then if that is the case, then you didn't try. Then you didn't follow the algorithm because the algorithm says you have to try out all possibilities. So apparently, the only way in which it could possibly fail to be complete is if you never derive the empty clause. So maybe, I don't know, maybe it's possible that although you apply the resolution rule everywhere you can, and although what you started with is unsatisfiable, this never gives rise to the empty clause. Okay, I'm going to argue that that can't happen, but first of all, we have to realize what it is that can't happen. Is that okay? So, why can't that happen? Well, there are lots of ways to think about this. I'll show you one way. So, when you prove something, it's typically so that there's more than one proof. But this, at least, is what we have to prove. We start with an unsatisfiable formula, but the empty clause is never derived. That can only happen if the resolution terminates before the empty clause is derived. In other words, there's no more pair of clashing clauses in my set that I haven't yet tried out. So, I'll briefly show you the argument. If this goes too fast to follow, then you can always read it in the book. This is actually for those of you who are really interested in this proof background. I will not ask you, say, the ability to reproduce a proof like this. So, it's not part of the exam to be able to write down a proof like this. But I hope that you're curious enough to stick with me here. I'm also doing this because it leads me to the next topic. So this again is a notion of tree that we're going to use here, but again, the trees stand for slightly different things. I will talk about a so-called semantic tree, and here we have a tree once more whose root is at the top, and at every level I try out all the possibilities for the next proposition. So, because all the possibilities mean either the proposition is true or it's false, it always branches. It's a binary tree which always fully branches. So it's a very large tree if you have a large number of propositions. But following a path from the root to a leaf gives you an interpretation, and every interpretation corresponds to such a path. Okay, now in this tree, if I have an unsatisfiable formula or clausal form, then every clause in that clausal form actually uniquely corresponds to, no, not uniquely, actually corresponds to certain nodes of this tree. So what, for instance, would this clause correspond to?
On the left side.
Yeah, so this is the clause where P must be true. So that is characterized by this node over here. I will call a failure node the shallowest node in the tree that falsifies some clause. Actually falsifies some clause. So actually the failure node for this clause is the node over here, where it's falsified. What would be the failure node corresponding to this clause over here, consisting of not P, Q? Well, yeah, it must be, apparently, P must be true, and Q must be false. So I follow the path until I meet P, not Q. That will be the failure node for that clause, yeah.
P should be false, or
no.
Q should be right.
In order to falsify this,
Oh,
P must be true and Q must be false. Yeah, because it says either P is false or Q is true. If neither is the case, then P is apparently true and Q is false, which corresponds to the node over here. What about the third clause, which says not R? Yeah, this is a bit more tricky because there are, of course, 4 nodes in which not R is falsified, and some of those nodes are below a node where already another clause was falsified, and that will then not be called a failure node. So I only call failure nodes those that are highest up in the tree and falsify some clause. So the full list of failure nodes in this example will be this node over here for the first clause, because there P must be false, so I go to the false for the P node, P clause. The second I already covered also, P must be true and Q must be false. Then what about the third? What is now a failure node for this clause over here?
All the way to the left.
Yeah, all the way to the left, because both or all 3 of the others were already covered by one of those other clauses. So that's only one of them left. And finally, I have the final clause which says not P, not Q, R. So in order to falsify it, must have P, Q, and not R. And indeed, now, what strikes you about this this tree? If I now draw in all the failure nodes?
Multiple solutions are falsified.
Yes. So whichever path I take from the root to a leaf, I will meet a failure node, which means that all the paths are not models of my clausal form. And that is actually something that you can easily see will always be the case if I start out with an unsatisfiable clausal form. If I draw the semantic tree in this way, then it must be the case that on all paths from the root to a leaf, I meet a failure node. If there were a path where I meet no failure node, that would be a satisfying interpretation. So the formula would not be unsatisfying. Yeah, so it's just one way to represent this, but what is being represented here is, well, an argument that this clausal form is unsatisfiable. So now let's think about what happens when I apply a resolution to a clausal form. Resolution takes 2 clauses and produces a new one. Yeah? The idea will be that whenever I do that, there will be another failure node in my semantic tree that is actually higher up than the failure nodes corresponding to the original clauses. Okay, in order to make that firm, I have to introduce the idea of an inference node. An inference node is just a term, right? So an inference node will mean a node that is the parent of 2 failure nodes. Yeah? So are there any inference nodes in my tree? First question. Are there inference nodes in my tree? Well, this example, you can see it. Yeah, there's an inference node. There is an inference node which is the parent of R, and not R over here, it's this node. When I apply resolution to the 2 children of an inference node, actually what will happen is that those 2 failure nodes will be replaced by 1 failure node, namely the parent, namely the inference node itself. When I apply resolution to to the clauses that gave rise to these two failure nodes, the clauses were not R and not P not Q are, if I apply a resolution there, what I end up with is not P not Q. The characteristic failure node of not P not Q is actually PQ, which is indeed in the tree the parent of my two original failure nodes. So, and that is something that is always the case. When I apply resolution to the clauses that gave rise to two failure nodes with a common parent, namely an inference node, then what happens in the corresponding semantic tree is that the two failure nodes are gone, are replaced by one failure node, which is the parent, the inference node. Yeah? And now we have the backbone of the proof of completeness. So if I take that parent, that inference node, as my new failure node, then of course you see that suddenly there's a new inference node, because this new failure node, together with number 2 over here that we already had, give rise to a new inference node. You can apply resolution there. And these two will be replaced by this one. And so on. Eventually, we end up at the root. So, quickly, the arguments are every path to a leaf contains exactly one failure node.